Okay, recording in progress. So, welcome back. We are continuing the conversation from last week because we only had half an hour, and also this time we will only have half an hour. How are you today? Let me ask you. I asked you already, but
Yeah, doing well. I've done with work for the week, so that's good.
I hope so. It's weekend.
Yeah, yeah, it is weekend, but yeah, we got a little bit of crazy stuff going around on the over the weekend. We have some weekend coverage from my team this week because yeah, the system's unstable and like no one else knows what to do,
Oh,
and we don't
so
really either. But yeah, yes,
so nobody else except your role, or
yeah. We're the only
oh, that's
people that
good.
like kind of, yes, yeah. But
I
it's
mean,
also like, yeah, when you're the only then people that can communicate on that topic, it's very rough, yeah.
yeah, I mean, it's responsibility, but it's also it means you're indispensable, or you're making yourself indispensable. That has advantages. It's like a double-edged sword, but I think it's like career path style. It's good, the good thing. So actually, let's back down a step. Can you actually reintroduce yourself and get to say a little bit about what we're going to talk about in the next 30 minutes?
Yes. So yeah, I'm Sean. I like studying math. That's one thing I like to do, and I really like the mathematics of fluid mechanics in particular. But I work as an engineer for semiconductor lithography, actually, for one of the companies that makes the EUV lithography tool for the manufacturing process that ultimately makes like advanced logic chips that
Yeah, I mean,
phones, computers use. Yeah.
last week you already introduced it like this, but I think people know this like company at least. I mean, I don't maybe I'm wrong, but I think the people who watch this channel like have heard of NVIDIA, ASML, and this kind of like a little bit of this chain. It's not like you
Yeah.
because this is the second time you're describing it in this super
Hmm.
abstract way, but I think like I guess people are close enough to that. And I will confirm that you really like fluid mechanics. I mean, you bring it up repeatedly, like
Hmm.
tangentially, like you always link me some papers that I don't have time to read,
Yeah. Yeah.
and oh, look at these cool things.
Yes.
So I guess you actually, I assume you at one point thought about maybe actually going into some fluid kind of stuff.
Yes. Yeah, I definitely did, especially yeah, in aerospace.
Hmm.
Yeah.
Yeah,
But
I
yeah.
mean, I while I was doing my PhD 10 years ago at the German Aerospace Center, that was of course very close to these kind of things. My roommate at the time, right, I was like, I don't know, I was 25. And he is a very solid engineer who worked on making planes less noisy on takeoff and on landing so that you can have it like
Yeah.
in an area with people and this kind of thing. So he did this sort of computer simulation stuff. So, it's a little bit similar to finite element methods and this kind of thing. So, I mean, you would surely love this. It's like a very practical and important application. And yeah, I mean, I have not talked with him since like a decade.
Hmm.
But that's sort of one of the access points. And I also like, I think fluid mechanics is it's fairly intricate. Like there's a lot of different things, and they're all fairly hard, I think. So it's an interesting thing that I never got like strong in that at all. Like the simulations I did during my PhD was like one dimensional, basically just in time.
Hmm.
You
Yeah, one
you had.
interesting thing you
uh
can if you look at the high resolution pictures of Jupiter, you can see all the like what in the gas clouds and whatnot. You can see every single kind of fluid mechanical instability that you might study in graduate school. Kelvin Helmholtz is there. Like there's the Eye of Kelvin. Like there's Cat's Eyes. There's the von Karman vortex streets. So there's this book called like the Van Dyke Album of Fluid Motion, and it has
Mhm.
these different kinds of instabilities. But then you could see all at once in one big thing. The yeah, in the Jupiter's yeah in the atmosphere there. But then a more earthly example in I think it's kind of a bit of a drive away from Seattle, Washington, but there's a place called Deception Pass where there's a very close island to the mainland, and there's a fast current of water that flows through that like small section,
Oh,
and
nice.
it produces a ton of fluid instabilities as well. So you can see those in nature, and that I really like to see the there's complicated math that makes yeah that they can describe those kind of instabilities.
Yeah,
Yeah.
I mean, my
Hmm.
understanding is that there is like this is one of the fields where there's actually a lot that people do not really like are capable of handling or maybe even not understand, right? So
Yeah.
this is interesting.
Yep.
And
It's still ongoing research, especially in three dimensions. Yeah.
mhm,
In two
yeah.
dimensions, at least, we've got our great proof by Olga, and I always mess up her
Hmm.
last name, Olga Ledeshanik, like Lady something, and yeah, she proved that there's at least the solutions to Navier-Stokes equation exist in 2D, but yeah, the 3D is the $1 million problem.
Was this
Yeah,
like is this a very old result? Like, I mean, I guess was it either at the beginning of the 20th century or more towards the end?
I think around the middle,
Okay.
yeah, around the middle of the 20th century, yeah, so around 1950 or something like that, yeah, so not that old, yeah.
Yeah, by the way, I just yesterday, like I saw a discussion online about, like, there is a book by Zizek, this philosopher guy coming out and he is going to incorporate like quantum mechanics into it. And I have not many hopes that this will be very coherent as far as the physics goes, and I find it a little bit annoying because I
Mhm.
actually listen to like I watched these Zizek movies and I started to read some books. Although if he goes into all this sublime concepts and so on, I'd never get far. But I'm not averse to that, and I would like to understand him better. I don't know how coherent it is, but in any case, so he's writing this philosophy book, and I mean, apparently he talks with Sean Carroll or something,
Yeah,
or at
okay,
least he talked with
nice.
him before. Yeah, I
Yeah.
mean I mean, but I know he has some interviews where he talks really like I would say bullshit stuff about quantum mechanics and like he talks by analogy. Okay, so in any case, some philosophers were like defending this, and then I saw online that people were like attacking the book a priori. And then I was thinking, what's very interesting is that physics, and I guess also it goes also for engineering, a little bit lesser for math, but um, I actually, I checked ChatGPT. What is actually the oldest book that, let's say, 98% of majors would actually read? Like, if you're starting to study physics the first 4 years,
Hmm.
what is realistically actually the oldest book? Because in philosophy, of course, right, you actually you will read some Plato. I mean, you will read some
Yeah.
2,500-year-old books.
Hmm.
And in physics, I mean, you don't. And so I was thinking about this kind of thing. What would you say is like I don't want to say research, but I looked into this a little bit and I have some candidates where I would stop in the time. What would you say is the oldest stuff that you would actually read in such degrees?
In physics or engineering,
Hmm.
hmm. When Halliday, Renzik, and Crane, my mother who studied physics, yeah, she also had the same book that I had. So you know what? In the US, they
So
give that one pretty
from when is
commonly.
this? From when is this? I mean,
That might be last century, 20th century, I think. Yeah, it's a modern book, but it's written about like classical physics.
20th century. So give me a date.
I think it's like right, it's got to be like 1970 or 80, I think. That's my guess.
Um, yeah, but that then is I mean, I would affirm that there's 70s books. I would even go
Yeah.
further because, of course, there's Landau Lifshitz, and which is from the
Yeah.
50s, I think.
Hmm.
So
Hmm.
this is basically like some very classical mechanics books from the Soviet times. But and there might be some, but usually it will be younger stuff. So it's actually like a stark difference between these fields where there is these fields where you basically read the originals forever. Like if you read Nietzsche, you will not like skip what Nietzsche wrote and just read what would be considered secondary literature. You will always go back to Nietzsche. Um, and whoever it is, right? I mean, I don't know how many people actually read Spinoza, but I guess some. But it's not like we are like reading Newton, let alone Hooker or something, right? So,
Hmm.
which is
Hmm.
interesting. I mean, you might borrow it from the library if they have it and actually
Yes.
look at it, but you already know that like this guy is lacking 200, 400 years or 300 years of mathematics, right? So it's
Yeah.
you won't learn from it in
And
that
it's
way.
gotten so much simpler because yeah, when Newton was
Yeah.
doing it, like if you look at some of his drawings in the
Mm-hmm.
Principia
Yeah, yeah.
Mathematica, there it's insane what he's drawing in there. But you can just now with modern vectors and vector analysis, you can do
Yeah.
in like one, two steps what he did in in many, many, many pages. Yes. Yeah.
Yeah, I mean, I have never really confirmed this, but I think even in physics in the 1910s, like 110 years ago, they didn't really like learn matrix calculus yet. Like this also
Mm-hmm.
was just coming later. I mean, in principle, this all goes back to some Chinese stuff, and it existed, but apparently, even though you would think linear transformations were always important in physics, they didn't really use it that much, not in this formulation. And I heard and read it a couple of times, but apparently like the Maxwell equations, they were originally like written down in quaternion form, which is crazy.
Oh, really?
Yes.
Oh, I didn't know that. That's
Yeah.
interesting. Huh.
Yeah.
What I heard was that they were very cumbersome when they were initially written, and that there were just many equations. And the
How
what we have
many?
now is the Maxwell. What I heard was something like
Yeah.
24 equations,
Hmm.
and then it was reduced to by Heaviside to the four that are commonly taught in like electrical engineering today. That's the legend that I heard.
Yeah, that's interesting, but I wouldn't know how that works. I mean, you say the
Yeah, neither
four,
do
but this
I.
is also, you say four, but it's also eight, really, if you don't count the vectors, right? It's like,
Okay.
just if you have the electric field and you write it down, it's not one equation. It's really
Uh-huh.
four, three,
Yeah.
right? Three things with number scalar. Let me say it like this: eight scalar equations, and
Hmm.
as you say, four if like in the way we write it down. Uh, and apparently there's this quaternion thing. But if you would have, what did you say, 18 or 21, 21 or something?
I think
Like,
what I heard the number was 24, but I've looked actually in Maxwell's treatise on electromagnetism, the
mhm.
1865 one, and I couldn't find that. So I don't know where
Yeah,
my teacher got that either.
yeah.
Yeah.
I mean, if you
Yeah.
introduce the vector potential, right, the
Hmm.
A
Hmm.
field, then you can probably get more. I would assume maybe there like if the gauge degrees of freedoms, the lambdas are explicit, then you have more degrees of freedoms. But yeah, I would still not know how to get to 14. That's some interesting history there.
Yeah.
Okay, so we are drifting away. I mean, I love this conversation. I love this topic in general. But maybe we like last time. Probably it's best you still repeat what you do, and I would like to get a feeling for how your day to day, like what you stress about, and how
Hmm.
that works in the company, from like the interaction. How much are you on your own, and like so people get an idea before we go to the implications of your work.
Yeah. So I guess very simply, if you want to land one feature of your circuit on top of another, you need to place it quite precisely, generally like within a few nanometers, ideally like within one. And that's actually what we've built the tool to do. We've built the tool to be able to land features. And these are features of ultimately a circuit that you're going to fire up. Because if you displace too far off and the then you fire the circuit at the end of line, you'll get a short circuit. It just won't go. So the electrical properties really depend on how you're placing individual features, and the way we do that layer to layer control is what we call overlay control, and that's my role there, within this whole set of things. Yeah.
And how is the stow control? Like, how do I imagine this? That there's like software which, while you do it, makes sure that you're not off, or how do you plan to not even have to correct? Like, how do I like, what are the tools so that I have an idea like with what you're working and what you worry about? Like, what does it mean if something goes wrong? What are the things involved in?
hmm So a little bit into the design of the tool, there's the reticle where you've actually got the pattern that you want that you've done with the e-beam lithography step ahead of this. And so that has the pattern on it, but the tool has this component called the reticle clamp that actually clamps onto that thing. And you're going to bounce light off of that, and then it'll go into a projection optic system of some kind. And that projection optic system will take that image and then project it onto the wafer level. So the and I just heard a very good description of it in the book called Chip War by Chris Miller. I've been reading it, and it's about how lithography started, which it was actually at Texas Instruments. They were doing semiconductor manufacturing, but they didn't have the lithography step yet. But they just looked via their microscope and they realized that what the microscope does is it makes a small thing look big up at the aperture where you go see the thing itself in the plane for viewing. But if you flipped a microscope upside down, what you would do was what you'd effectively do out of that would be making a big thing smaller. And they actually did that, and they started the first lithography process based on just a flipped microscope, effectively. And what you have control of then is your object plane, your image plane, and protect potentially the aberration profile in your projection optic system. So there's a certain set of polynomials called the Zernike polynomials that describe how the optical phase error distorts points and images, and we actually have mechanisms to control that. And you can control the object plane and the image plane during the scan. So your controllers are basically placing the image with these degrees of freedom.
Yeah, I'm not sure if I can like without any visuals see that in my head. Like I'm thinking like these the moving parts, are they like what is the mechanical mechanism that shifts things around and moves and holds things stable, and how do you correct that? Like, is this like, do you have a small controller and then there's some software or Python where you say, oh, move to the left, or is this completely automated that you like adjust things and move things together when you start and move the lens around?
It is all very automated, and at the end of the day, you place within nanometers, but there's also feedback that you do offline. You go measure how far you're still displaced with a metrology tool. So there's also a whole suite of how you're going to actually measure how far you're placing on average a misplacement. And you can feed that back as well to try and go even better. And that's additional kind of mechanism of my role is that there's the product overlay control
And
from that
like,
aspect. Yeah.
are you more like in the future devices, or are you checking things that are already like being produced?
It's being produced now. Uh, let's see, let me try and remember what are we calling? Oh yeah, I think the publicly known name is actually the 18A process for Intel. That is going to be that line of products that's going to be produced. And then what we already have in high volume and is at Ireland is the Intel 3 nanometer process. So yeah, that produces a particular product line. So the first one that I worked on was the 14th generation of Intel products. So we got the control working for that well enough. There's actually still ongoing improvements even for that process. But now the one we're going for the products that's going to be released first half of next year by Intel, that's being defined now and finished up.
And do you have like a different, completely different process for every device? Like, in what do different models, let's say, change what you actually have to do with the big machine?
hmm Yeah. So depending on that depends on exactly what the technology is changing. Between the Intel 3 and the Intel 18A, there's two major changes. There's a big change in the transistor design, and I don't know many details about this, but it's going from the FinFET transistor to the gate all around transistor. So actually, like how the gate, the source, and the drain are arranged, that's actually different in the transistor in this
Hmm.
time. And I think this is the first process node for a high volume that's really going to bring that in. And over in Taiwan, we have TSMC working on the 2 nanometer that's also going to do the same transistor design, gate all around, they call it. And the other major change with this one is they do the backside power delivery. So instead of having the signal routing from the source and drain of transistor and the power in the same layers there, to increase the density, you separate those out. So there's actually a step where you've built up all of your signal routing now. You need to now flip the wafer around,
Hmm.
and then you're gonna bond to it the where the power is gonna be clicking into the transistor.
It's like
So
cooking
this
an egg.
actually
You're
totally
flipping it.
yeah, so this is something Intel will do with another tool. I forgot the vendor of that, but this then when it comes to our tool is going to be like distorted potentially by like
Hmm.
100 nanometers or something. So we got to measure that distortion and know how much it is and get capture that average effect.
And
And
then
yeah,
you program a tool which does it, like, because in the end, there will be billion of this little devices being made, right? And so your program that everything like corrects automatically, and this gets, I mean, I have a vague understanding like these things come in, and then there's automatically an adjustment, I suppose, and you're responsible for coding up this whole process that it works on its own when it is being fabricated, or
I'm not actually part of the development team that codes this even. So
uh-huh.
there's in the Netherlands, there's a bunch of people that actually that are real programmers, so to say.
Yeah.
I'm as an applications engineer, I'm like a step ahead to try and figure out what Intel's even going to need to implement.
And you do
Yeah.
this by like you get test samples from these small things, and then you see what works and what doesn't, and what fails. You have like one run with one device, and you see where are the problems. Do I imagine this correctly?
Yeah, so the fundamental data we actually get, what overlay data is between one layer and another layer, we get a vector field of a bunch of points where we actually measured how displaced it is, to get an
Um.
idea of what are the, and then there's some characteristic fingerprints to this. Like the field fingerprint is one generally that, okay, the lithography tool itself made some kind of error. So what one kind of phenomena that can make that is heating of the projection optics that can distort the aberration profile in such a way
Hmm.
that you have this phase error that every field you'll have a displacement that looks like a magnification of the image. So this is one kind of physical phenomena that can then produce a fingerprint that's then recognizable in the data as a physical effect. Yeah.
I see. And this is this a little bit like sort of distortion everywhere, and so this vector field is like on every position how the displacement there typically is in your process. It's like
Uh,
pointing in a direction in which it is like accidentally moved, or
yes, is a is measuring that displacement. Yeah,
hmm
but
hmm
that is also very dependent on what use case you're running, because depending on what you have at reticle level and depending on also what illumination profile you use to try and illuminate the light. So that's another degree of freedom, actually, that I forgot to mention, which is your illumination profile. We also have a, a capability to adjust. And it's Carl Zeiss over in the Germany who really makes this illuminator and the projection optics for the system that gives us a lot of capability there.
hmm
And with that, you get different physical effects occurring. So if you have a reticle that has more transmission ultimately, and you're running at a higher energy level, then you're going to heat up your projection optics more. Those are the kind of use cases which will stress that physical effect more. So if you want to catch a certain kind of effect, how that characteristically looks, you can kind of make experiments. And these are the also
Hmm.
the kind of things as an applications engineer, I'm going to try and look at Intel's process, look at the other customer's process if I'm supporting them at the time, and then try and come up with experiments where we can induce those effects even and see if we're robust to them or if we need to come up with some custom control strategies for those. Yeah.
Okay, okay. So you are sort of a data collecting machine and see which non expected behaviors lead to which sort of displacements, and you tell them this is the worst thing to do and this is okay if you do. I, do I imagine
Yeah.
that's correctly?
Yep.
I see, I
And
see.
then
Okay.
there's another level, the actually at our customers, they themselves have their own layer of customers, like NVIDIA and the final end chip designers that are asking for these chips to be made. They ask TSMC, or yeah, Intel Chip Design asks Intel Foundry, okay, we need to make a chip with these specifications, but the manufacturer actually has to go back and tell them what are the design constraints that are possible. So there's something called a PDK, and I think it's like product development kit that translates ultimately like what kind of circuits are possible to be printed. And then the manufacturer actually doesn't have direct knowledge of what the logical structures in the chip are that way.
Hmm.
There's just a set of design rules that are said that, okay, we can't print something tighter than this dimension in this kind of layer for, like, say, if we need a metal layer placement or we need a via layer. There's different types of layer constraints with
What are
different
these
kinds of shapes
layers?
that you want to make.
Metal and layer? What did you just mention? Which layers?
Metal and via. So metal is usually like grating type structures, and vias are like some holes that you want to place some array of holes. Yeah, oftentimes they look like that. And then at the transistor layer, which is generally like low down, there's all sorts of crazy random logic structures. So there can be really full 2D designs there. So that's how I envision it. But I also have never done the process of doing the full like design of a product kit there that
Are
then goes
you
to a
close
customer. Yeah.
enough to these things that you're actually like wearing a coat, or how do I imagine you day to day, or are you sitting
Oh
in front of a
yes.
computer?
Day to day, I generally am in front of a computer. But I've been going this year maybe a couple times into the fabrication environment to run some custom experiments.
Mm-hmm.
So yeah, my customer is actually like Intel in particular is very willing when I come up with one of these experiments to let me in on the tool and run the
Okay.
tool. So that's actually been very fun to go in and then heat up the wafer and see the wafer heating. Like when the yeah when I induce an effect and then I'm able to see that in the overlay data, that's very very entertaining to me, and it's great that actually Intel allows that. Yeah,
Yeah. What,
yeah.
what do you actually see? I imagine this is like a small thing, and I mean, what do you mean see the effect? What does it look like?
Yeah, well, to see it, we have to measure it with, yeah, with the overlay metrology of some kind. So
Mm-hmm.
we just see a vector field. Outside of the tool, like operating it, it's just a big box, and you just hear stuff scanning in there. You can't really tell what's going
Yeah.
on. And there's a little GUI on the thing. I don't know if this is publicly available, like what the GUI looks like, but it shows the wafer on it, and then it shows like the fields
Okay.
being scanned
Yeah.
on there. Yeah. So it's pretty
Okay.
entertaining to watch
So
the
actually,
GUI.
this
Yeah.
is like you were talking about these displacement vectors and stuff.
Yeah.
And this is actually a little. Firstly, I imagine these plots look quite fluid dynamic-ish, right? I could
Uh-huh. Yep.
imagine.
Yep. Yep. Yeah. It's like a 2D fluid mechanics problem.
Exactly. So
Yeah.
you're
Yeah.
home
Uh-huh.
there. And
Yes. Yes.
also, like I never got too deep into it. I had like one lecture during my master's thesis or my magister thesis, where it was actually about like elastic bodies, which is like a very like a specific field. I think not everybody who will study physics will actually see that how like bodies which are not rigid, you do not use the rigid mechanics and the generalizations of all the Newton equations and so on, but you have actually like materials which can like squeeze together, and then you have this various like electricity, this
Elasticity.
elasticity module
Yes, yes,
exactly.
yes, that's the word. Yes.
And there is like I was like I think 2 or 3 years ago I had a book from the library which was about like bands and basically about sticks. You have one stick and it can bend a little bit like a spaghetti. And the math is like it's very like Riemann geometry style. Like it's a lot of like you have this tensors, and it is actually quite fancy. And of course it is related to very early like um the string generalizations of your classical harmonic oscillator generalizations and this kind of thing. So this displacement vectors also play a huge role there, and I'm thinking about this. So I think it is. Firstly, I think this topic would interest you, even if I don't work with these macroscopic objects. Maybe I'll link you some stuff. But also, yeah, I can see how you have your fun with that. I would want to
Yes.
just mention two more things. Firstly, I have been in Jena this year actually, and there is this. Do you know the how the city looks like? There's this tower in the middle.
I don't know the tower. I see some of the architecture, so I know like some of the buildings, but the
Hmm.
tower I don't remember. Yeah, in Vienna.
In not in Vienna, in Jena where
Jena.
Zeiss is. Jena, yeah. Also,
Jena. Oh, Jena, Germany.
yes, yes, yeah, exactly.
Oh, okay, okay, okay.
So
No,
it's
I don't know what it
basically
looks like.
it's a fairly old town or city.
Hmm.
I think like I don't know 100 200,000 people maybe, and there is like a skyscraper in the middle which is called Zeiss Tower I think, and actually they bought it or they had it built Zeiss. And then they discovered that it was shaking too much for their experiments, and so they abandoned it. And so you have
Oh,
this one thing sticking out of this old city, and
uh-huh.
the actual size, like the labs, are somewhere else now, also in Jena. But
Wow.
yeah, but this is like there's a
That's
little bit of
crazy.
a
Wow.
fun
Those
fact
two.
story.
Yeah.
And also, like I don't know if you noticed, but this is something I always love to tell people that there's in physics you have this stress tensor, stress energy tensor,
Hmm.
right? And there is a little bit like a linguistic problem with that because it's like it's like a rip in peace because you actually you're saying basically tension twice because tensor this was like the first object and it's already about stress, like it's about tension tensor.
Yes,
So if you
yes.
say
Hmm.
stress tensor, it's like you say the same thing twice, right?
Yeah. Hmm.
So there's this funny thing, but yeah, people will not get rid of that. Okay, so I don't know if you see it on your side, but again, we're running out of time again.